Okay. In the last class, I missed something. I talked about completion. Or just he reminded me. I mean, we have a metric space. Well, it's just I want to just mention this. We have a metric space. Then we took all the Cauchy sequence in X, and then we had an equivalence relation. We quotiented with the equivalence relation. Then we called this as the completion X bar. Then we verified that we had a map, just constant sequence, X into X bar, and which is just constant sequence, X going to XXX, constant sequence. Then we showed that phi of the range is dense here. And I forgot to show that this is actually complete. But this is very easy, but I forgot to show, I mean, it's very easy, but I forgot to show that this is complete. So the claim is the X bar is complete. To prove this, we just have to prove that if we have a sequence Xn, to prove this, we have to take a sequence in Xn, we have to show a limit, there is a limit there. For that, it is enough to show, there is enough to show, enough to prove. This is the claim actually. Enough to prove for all Cauchy sequence Xn, Cauchy, there exists a limit in X bar. It's enough to show this. Why it is enough to show this? The reason. So if we have a so we have, I mean, if we assume that we have shown this, okay, we have shown that for Cauchy sequence here, there is a limit here. We have to show for any Cauchy sequence here, there is a limit. So suppose Yn is a Cauchy sequence, Cauchy, and Yn is contained in X bar. Okay, then you can choose Xn because that is dense there. Phi of X is dense there for any, sorry, phi of X. I mean, if you want to be correct, it's not, it's X is correct. I mean, by calling it X is correct, but we are identifying X inside the X bar, so it should be called as phi of X. Okay. So choose Xn in phi of X such that we have already shown that that is dense there, such that d of Xn Yn is less than 1 by n. Okay. Okay. Now that has a limit. Now Xn converges to some X in X bar. Okay, something. Okay. Now d of Yn X is less than or equal to d of Yn Xn, which is less than 1 by n, plus d of, I mean, the Xn is also a Cauchy sequence we have to show. Xn is a Cauchy sequence because d of Xn Xm is less than or equal to d of Xn Yn plus d of Yn Ym plus d of Ym Xn. Okay. Because of that, Xn is also a Cauchy sequence. I'm taking a Cauchy sequence in X bar. This is the reason for that. I'm taking a Cauchy sequence in X bar. Okay. I want to show that that is, if we see, I'm saying that we want to prove that X bar is complete. To show that, I'm saying that it is enough to prove for all Cauchy sequence in X, there is a limit. It is enough to show that. I'm only giving the reason for that. Okay. Proving this claim. Okay. So suppose if we have a Cauchy sequence in X bar, then we can take a Cauchy sequence in phi of X such that they will have the same limit. That's what I want to show. So for that, if we have a Cauchy sequence in X bar, we can choose a Yn because it is dense there. We can choose a, we have a Yn there. So we can choose an Xn such that this is less than 1 by n because it is dense there. So once we have chosen, this Xn is also Cauchy because of this inequality. I mean, again and again, triangle inequality. D of Xn Xm, okay. Because of this, Xn is also Cauchy sequence. Maybe I will write it if you are getting confused. So because this will imply that Xn is also Cauchy. Okay. This is okay. This implies Xn is Cauchy. So Xn converges to some X in X bar. Now the claim is Yn also converges to the same X. That's why. So d of Yn X is less than or equal to d of Xn Yn plus d of Xn X. That's all. Okay. Because of this, it follows that Yn also goes to X. Okay, this is okay. Anyway, this should be an exercise. So that is the reason for that. Okay. I mean, we have proved the claim. Now, after the claim, now if Xn contained in phi of x is Cauchy. Okay, but xn is equal to some xn hat, right? I mean, x. Now let's call it phi of xn. Now phi of xn contained in phi of x is a Cauchy sequence. Okay, this if xn is a Cauchy sequence, then if I get xn is Cauchy. Okay, I leave it as an exercise. Okay, this is the idea. Xn is Cauchy. Xn is, I mean, anything here will be a phi of xn, so it will just consist of constant sequences. Okay, so xn is so if phi of xn is contained in that, then we have xn. So if this phi of xn is Cauchy, that means this xn should be originally Cauchy. You can just write down the distance; it will follow. Now you take that sequence itself. Now you take x bar is equal to this x1, x2, this sequence itself. Okay. Now exercise. I mean, the same thing, you just write the definition, it will follow. Okay, now this d of xn, phi of xn, this x bar will go to 0. Okay, that's all. I mean, these are all very easy. I just didn't do it last time. I forgot to do it. So this is the proof. Okay. Anyway, we will give, I mean, any doubt? Huh? X bar is it is just a Cauchy sequence. You start with a Cauchy sequence phi of xn. Okay, so phi of xn gives the information about xn. This is just a constant. Each phi of xn is a constant sequence, right? This is a sequence of sequences. Okay, but where each phi of xn is a constant sequence. So you have an xn. That xn you collect it, that gives a sequence. Because that is Cauchy, this will be Cauchy. Since this is a Cauchy, this is an element of that x bar. That is just a Cauchy sequence. Then this will converge to that. It is just the detailing. There are too much detailing, but proof is very simple. Okay, it's better you sit down and write. Yeah. Don't say. He is asking. Finish. What, say it again? Yeah, correct. No, that is, I'm proving the claim. Enough to prove. First, I'm proving a claim is there. Enough to prove that this is the for Cauchy sequence in P of x, there is a limit. That will imply, then the claim is that will imply for any for one. Okay, now we want to prove that for any, I mean, whatever is contained in the claim. For any xn in phi of x, there is a limit. There are two steps. First, we prove that statement. Hmm? Yeah. So because xn is there, it converges. Because we are assuming every Cauchy, the claim is, let's be clear, the claim is if it is enough to prove this is Cauchy. If this is Cauchy, there is a limit in x bar. That will imply for any sequence in x bar, there is a limit. Okay, for anything in phi of x, any Cauchy sequence in phi of x, there is a limit. It is enough to prove for anything in x bar, there is a limit. So assume there is a for any sequence here, there is a limit. So I take a sequence in y bar, I take a corresponding sequence in xn by getting something by this approximation. Because then I prove by this inequality that is Cauchy. Because that is Cauchy, that has a limit. Because that is our assumption. And that limit is same as this limit. That's all. That's what I have written. Now to prove this for everything here there is a limit. Here you have a Cauchy sequence, so which is just the sequence of constant sequences. Sequence of constant sequences. So you take that sequence itself, xn itself. That is a Cauchy sequence. Prove that, I mean, this is very easy. Prove that converges, this constant sequence will converge to that. You just write the definition of the limit, it will follow. Okay, that's all. Correct, no? Yeah, which is right. Here, here. Now I mean, this claim is proved. Okay, this claim, hence the claim. Okay. I actually wanted to give this an assignment, but it's okay. Hence the claim. Claim is okay. Now we have to prove what is context. Enough to prove this, so we have to prove that, right? It's enough to prove, that's what we have proved. So we have to prove that. So that proof is, that proof is, if we Cauchy sequence here, that has a limit. So I take a Cauchy sequence here, phi of xn. Phi of xn comes with an xn. Phi of xn is nothing but xn, 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 xn. That's the sequence. So you have an xn. So from that xn, you construct this xn sequence, x1, x2. Now the claim is this phi of xn, which is a sequence in phi of x, converts to the, now this is one single element, right? This is an x bar, one single element. Now this phi of xn will converge to this. Okay, just write down the statement, which is just you take the distance between the nth element. Nth element is going to be just xn itself. And here, I mean, you just take the xn and some xm greater than that will go to 0 by the definition of quotientness. Okay, that's all. Okay. So we have proved that ball bound. So we have proved all bounded sequences are complete. So L infinity m, which is just nothing but b of n. I mean all bounded functions in n. So this is complete among the sequence space. So now I will prove that L1 is complete. L1 of n, okay, is complete. Okay, so I leave it as an exercise for L. The proof is same. L2 is complete. Okay, I leave it as proof. So L1 is complete. What does it mean? To take a sequence. Each xn bar is a sequence. Okay, xn bar contains L1. Okay? To take something in Cauchy, we have to prove that every Cauchy sequence in L1n. L1n, each element is a sequence. A Cauchy sequence is a sequence of sequences. Okay, so I take xn bar. Each xn bar is a L1 sequence. Okay, then I take a sequence like this, n equal to 1 to infinity. This is a Cauchy sequence. I have to get a limit for that. Huh? Right. Xn bar is an element here. Okay. Each xn bar is an element here. The sequence is a subset here. I mean, subset means not exactly this notation. There is a problem if you realize. Yeah. Sequence of sequences. Okay. Where xn bar equal to x, I put xn k equal to 1 to infinity. Okay. Each one is a sequence. Okay. Now this is Cauchy. That means limit nm going to infinity, norm of xn bar minus xm bar goes to 0. The norm one norm, okay, goes to 0 as n and m goes to 0. N and m goes to infinity. But this is equal to summation mod of xn minus xm k. Okay. Okay, this goes to 0 as n and m goes to 0. Okay. Right? That's what it means. This is just the definition of this. Okay. This is just the definition of this. So this goes to 0. So the sum goes to 0. They are all positive elements. So each element should go to 0. Okay. So this implies xn, xkn minus xk m 0 as n and m goes to infinity. Okay. This shows that for each k, this is a Cauchy sequence. Okay. xkn is Cauchy. K equal to 1 to infinity is Cauchy. Right? That's what this says. Right? So, but these are all in complex number or real number, depending upon what you take. So there exists a limit. So there exists, this is in xn. This is in once again. Is it in n? Is Cauchy in, sorry, xk. This is, wait a minute, sorry, n. It should be in n, sorry. This is as n and m goes to 0. So for each k, this is true. Right? N equal to 1 to infinity. Huh? K is fixed. Yeah, k is fixed. Each k, this is going to 0 means for each fixed k, this is Cauchy. Yeah, I wrote it wrong. Okay. So there exists an xk in real line or complex number or real line, doesn't matter, whatever you take, such that x and k converges to xk as n goes to infinity. Okay. Now we have to prove two things, claim. We have to prove two things. To prove that it is complete, we have to find a limit for this sequence in L1. So for that, we have to prove two things. One is this xk, k equal to 1 to infinity, is in L1, number one. Okay. And this xn bar, okay, this I call it x, okay, x bar. I call it x bar. Okay. Now xn k converges to this x bar in L1. These are the two things we have to prove. Okay. I took a sequence in L1. Okay. Then I wrote the definition of its Cauchy in L1 in this topology. That means for each k that, I mean, the coordinate, whatever you call it as a coordinate of the sequence, that goes to 0. That is Cauchy. So there exists a limit for each coordinate. Okay. When you fix the k is the coordinate. For each k, there is a limit. I take that limit. Okay. So for each k, we have got something. You call that as x bar. Now I have to prove that this x bar is number one, it is in L1. Number two, it has to converge in L1. These are the two things I have to prove. Okay. So that is the same trick which we have already done. Yeah. There exists an, xn, no. xk in C or R, I said. It can be C or R. I mean, there exists, okay. This is okay. There exists, you have a field, k if you want. Here, this is C or R. There exists in xk. There is this is Cauchy in C or R, so there exists in xk. That's all. Huh? Yeah, kth sequence. Yeah, you have array. It's just the kth one. Yeah. Yeah. No, instead of coordinate, you consider as a coordinate kind of thing. It is whole thing is Cauchy. Each coordinate converges. It's the same proof. There is nothing in Rn. That's how will you prove Rn is complete? If there is a Cauchy sequence in Rn, then each coordinate will converge, and it's like that. I'm just saying each coordinate is convergent. Nothing else. Each coordinate is Cauchy. So there is a limit for each coordinate. So that's what I have taken. No confusion. Okay. The subtlety comes here. So you should listen here, maybe. That's very easy. Okay. Now we have to prove the claim number one is whatever we have got xk k equal to infinity is L1. It is actually, you can take epsilon and other things and prove this, but I give an argument which is essentially same. I mean, it's the same thing, but I mean, most books will use take an epsilon and prove that, I mean, prove that it is in L1 by something. Okay, but rather I will use this. What I do is the following: I have to prove that summation xk, this is less than infinity, k equal to 1 to infinity is less than to 1 to n. Okay. Now this is less than or equal to summation k equal to 1 to n. Okay. Xk minus x n k plus summation some n naught k. I will choose naught. Okay. N naught k and summation n k equal to 1 n x n naught k. This is okay. This is triangle inequality. I can choose any number. I can insert any number here. I'm just inserting x and naught. Okay. X. Now this is exactly equal to limit m going to infinity. If you wish, this is just a finitely many of them, right? I'm not taking infinitely many of them. Just a finite sum for some n. Huh? This one is. I'm just going to the next step. That's all. Huh? Any n. Any n for any n. Okay. This is xk m minus xk n naught. Okay. Plus whatever k equal to 1 to n x n naught k. This inequality, what is it? You can insert any number here and write this. Yeah, I'm just instead I'm just taking some x and not k. I will choose n naught. I will choose this n also arbitrary. That n is n naught is also for the time being arbitrary. Okay, that's all. Okay. Now that I'm just taking limit here. This is just a finite sum. So I mean, if it is infinite sum, you can't do it. So it's just a finite sum till now. Huh? Xk? Yeah, that is limit. Xk is just the limit of this, no? That's how we have chosen x. X is just the limit of that in M. Since it is a, that's why I'm saying, since it is a finite sum, I can do this. You should remember. If it is infinite sum, I will not do this. There are two infinity, you cannot do that. Okay, since it's a finite sum, I can do this at this level. Okay. Okay. Otherwise, you should argue with epsilon and other things. Just an argument. Okay. Now this is less than or equal to limit m going to infinity, which of course exists. Norm of xm bar minus xn naught bar plus whatever, plus the same thing. Okay. Same whatever. You can take, I mean, this is for any n. For every n, this is less than this. Provided this limit exists, this is okay. This limit exists because it's Cauchy. Okay. Okay. Now you fix an n naught, this will be less than k. Choose any n naught so that this is less than epsilon naught, such that xm minus xm bar minus xn naught bar is less than epsilon for all m greater than or equal to n naught. Because it's Cauchy, this is true. Because it's Cauchy, this is true. Okay. This is norm 1. I mean, this is one norm. That, I mean, up to infinity is this norm. If you take n up to infinity, it is this norm. Okay. So anyway, this is smaller than this. And as far as this limit exists, this is okay. Okay. So I am taking n naught is something. After that, this is less than epsilon because it's Cauchy. Okay. So that will be less than epsilon. For this fixed n naught, there is a k naught. So this whole thing is less than or equal to some epsilon plus L1 norm of 1. Okay. That's all. So it is in L1. This is just a number. This is just epsilon. Yeah. This part. This part. This line. No. Here I have this. Because it is Cauchy, after some n naught, this will become for all, this will become less than epsilon, right? N naught, after some n naught, this will be less than that for all m. Okay, because you are just taking limit, it's fine. It's okay. So that's why I'm saying this is less than epsilon. And here, this is just up to finitely many. This is one. When you take up to infinity, this is what you get. This. When n is, you take sum up to infinity, you get this. So they're positive numbers. So we are also using that fact. They are all positive. So this is less than this. So it's okay. What? Partial sum. Because I can't do this. I can't take this limit. The limit is in, see, xmk converges to xm. So you have a limit m here, but you can't take the limit outside if it is infinite sum freely. So I am taking partial sum, but I only want the inequalities. But no, wait. So till now this is true. Okay, this is less than this. Action k equal to 1 to xk. So you have to write this is less than or equal to epsilon plus norm xn naught bar. Okay, for all n. Okay, this is the argument. So now you take limit infinity. So this implies norm of x bar 1 is less than or equal to, I mean, norm of x bar 1 is, and this is some infinities k equal to 1 to n summation xk is less than infinity. Okay, that's all. So it is in L1. Okay. If you want, so this implies the sequence xk k equal to 1 to infinity is in L1. This is okay. Where is n naught? You can insert anything you want, and finally we are choosing n naught. Yes. Insert any number here. It will work. Yeah. This is the upper bound for this. second term. This is anyway less than epsilon after some time. So xn naught we are choosing here. Choose n naught. Yes. Yeah. Correct. Yeah, of course. Say it again. No. I am using the fact that n naught different from what? N naught only depends on epsilon. I am choosing the fact that this is Cauchy. That means this is this Cauchy in L1 norm. Because of that, I can choose this n naught for all k. That doesn't depend on k. I mean, this norm itself is less than epsilon because it's Cauchy in L1. Because of that, I can do that. Okay. Okay. Fortunately, it's being recorded, so you can get convinced by looking at it, looking at the video again. Okay. Here, xk we have defined it like that, no? Xk limits of x and k as n goes to infinity. We started with the sequence in L1, which is Cauchy. We showed that it coordinate wise converges. That coordinate wise limit is xk. For each k, there is a limit. So we got a sequence xk. We have to show that sequence in L1. That's what I have shown till now. Now I have to show the convergence happens in L1. Okay, I didn't understand what you said, but if you have understood, it's fine. Yes. Before where? Where? Started with what? Yeah. What is the exact symbol? There is no exact. We want to show that this has a bound for all n. That's what we have shown. There is no this. We don't know a priori this has a bound for all n. This sum converges as n goes to infinity. That is this sum, absolute sum. That converges is what we want to show. That's what we have shown. For all n, this is bounded by one single number, which depends on this n naught and epsilon, which we have chosen. Okay. Fine. Okay. Now we want to show next claim is we have shown that xk, whatever the sequence you have got is in L1. Now we want to show that x bar, xn bar converges to x bar in L1. Okay. Now we have to show this. Again, the same idea I am going to use, nothing else. Okay. Yeah, it's better you be very careful with these things. I mean, these arguments, this inequality and taking limits and all that. Once you are used to it, I mean, yeah, it will. If you are going to do mathematics, any kind of mathematics, okay, it's not just you do research in mathematics. Okay, you do some AI which is based on mathematics. So there also you need all these things. Of course, you should be very careful about that, right? These inequalities, limit, and all that will come whenever you do mathematics, any kind of mathematics, applied mathematics or anything. Okay, so maybe not L1, but all these things, these ideas. Okay. So now shall I prove this? Xn converges to x1. Okay, xn converges to x bar. Okay, to prove this, what do we have to prove? We have to prove that we have to take this xn k minus xk, k equal to again 1 to n. This should go to 0 as n goes to infinity. Okay, we need to prove. Okay, need to prove. I mean, that's what we will prove. So I am not writing it. I am just telling you. We need to prove that this goes to 0 as capital N goes to infinity. That's what we have to prove. That's what it means by convergence in L1. This bar we need to prove bar minus x bar is goes to 0 as n goes to infinity. Okay, so we have n here, we have summed over k, we have a n here. If you take up to infinity, that is the norm of this, that goes to 0. That's what we have to. Okay, that norm exists. Okay. We have already proved that this is in L1. Okay, we have to show that this is equal. Okay, now this is equal to limit, again the same idea, m going to infinity, summation k equal to 1 to n. I'm taking finite sum because I'm writing the limit outside. You can take a limit here that will become xm, m going to infinity. Okay, this is m going to infinity. Then I can take the limit outside, so that's why I'm writing a finite sum, okay, for any m. So this xkn minus xkm. This is okay. Okay, now it's done, right? Now this is then or equal to limit infinity norm of, I mean, if it up to infinity. This is true for all n. This thing is less than if you take the whole sum, right? This is, I mean, if it, which is same as xn bar minus xn bar. Okay. Now, if you want limit n going limit equal to less than or equal to limit, these are all positive, so you can write it limit n. This is precisely what it means by Cauchy. This is equal to 0. Okay. Forget about limit n going to infinity, you can write it finally. So I'm just having limit n going to infinity, limit m going, there is no m here, then I insert m here. Okay. Then I write the whole thing. This is less than or equal to that. Yeah. It is easier. I am just saying that limit n going to infinity, this is as capital N, no, no. Okay, this is equal to 0. This implies, okay, uh, you can take limit n going to infinity here. That's what you want to do. Okay, that's your question. For each n, this goes to 0. I mean, so okay, this goes to infinity, this goes to 0. This means I'm just saying that summation k equal to 1 to infinity n, limit n going to infinity, xkn minus xk, this is less than epsilon for all, maybe n naught, for all n greater than or equal to n naught. Okay, that's what this says, right? For all n, for all, no, no, wait a minute. For all n that is less than this, so you can take the limit. I mean, forget about this. You don't need all that epsilon, epsilon. You have this for all n. Okay, for all n this is true. So limit going to that is also infinity. Something is less than epsilon for all n. So the limit will also less than epsilon for all epsilon, right? So that goes to 0. This is less than epsilon. Okay, okay, wait. Hmm. Okay, you don't want to take, okay, maybe I will do this. Okay, don't take the limit here, okay? That will work. Now this is okay. Okay, it's good. Okay, this is okay. Now this implies summation k equal to 1 to infinity xk n minus xk. Okay, this goes to 0 as n goes to infinity, right? Wait. Summation, no, this, wait. Limit, wait. That will be less than epsilon. One second. So I have summation k equal to 1 to n, this, which is m equal to this, up to here, this is fine. This is not equal to 0. Okay. This will be less than, for all, this will be less than epsilon after some time. As m, that is what I, true. No, but he wants to conclude something. He thinks that there is an exchange of n and n, right? You believe so, which is not the case. That's what I am trying to say. No, what I wrote, everything was right, whatever. But the final conclusion, he is thinking that there is a n, I mean, because n is inside, L limit n is outside. So I thought he thinks that I am taking a limit later. Okay. Okay.
Take it on in capital N from second.
Yeah. I mean, that will mean it's less than epsilon. That's right. Correct. Yeah, that's where somewhere we should. So yeah, you are right. So we have this till here it is clear. This is less than epsilon for all n greater than something. Mm. No, no. So, so this implies summation k equal to 1 to infinity summation xkn minus x is less than or equal to what? Uh, here I'm exchanging infinity. That's okay. You are asking? Yeah, because it's finite sum. No, so I'm doing. Here there is no problem. Only infinite sum there is a problem. It's finite sum, so I'm doing this. Okay. So this is let
Now you can take the inequality.
yeah. Now this is
Capital N.
now this can be made I mean up to this n. Uh, yeah, I keep the n as it is. Epsilon for I mean this is less than epsilon for all. No, yeah. No. We just have a limit and m going to infinity. So this is less than epsilon. That's fine. This is less than epsilon for all n. That's all right, no? Why do you have to take? Huh? This is less than epsilon for all n greater than n. Okay. And for all n. Now you take limit n going to infinity first. And that is the statement we want. Okay. Now limit n going, this implies summation k equal to 1 to n, n infinity, summation xkn minus xk is less than epsilon for all n greater than or equal to n. That is what precisely the meaning of limit of that going to 0. Now this is, I think, let me write it and then come to now n going to infinity, norm of xn bar minus x bar, 1 goes to 0. Wait. I have taken a finite sum. I have inserted a limit here, taken it outside. So limit m here. So this goes to 0. I mean, now what I want to say? Yeah, this is less than epsilon after some time, after some n. Now this for all n, this is less than epsilon. I take n equal to infinity, n goes to infinity. So this is less than epsilon. Okay, for all n greater than or equal to n, that's what it is. Because I'm using the fact that that is Cauchy. This is one norm. Maybe I should write it separately and then, I mean, first write this and then this is less than this for all n greater than some n naught. Finally, I'm taking here. Small n goes to infinity, I'm not taking. This is the final step, I'm just concluding. I have this, this is equal to, this is, I mean, this is just the limit equal to this, okay. Now, whatever we have, I mean, these things are less than this norm, and we have this is a Cauchy sequence, so this will go to 0 as n and m goes to infinity. So from that, I am concluding after some time, after some n greater than m naught, this is less than epsilon for all n. Now we take the infinity, n going to infinity. So this is less, this whole thing is less than epsilon. Okay. And that is precisely means this goes to 0. What is equal to 0? If the n is there, no, since there is no equal to 0. Limit n, I am not writing n goes to 0. Here, yeah, limit infinity goes to 0. Oh, sorry. Yeah. When I write the limit, it should be equal to 0. Correct. That's all. Okay, this is fine. So it's very short, but we went through it in all detail. Okay. So yeah, we took so much time, but that's okay. Have you done this before in this detail? Then it is good. Similarly, you do this for L2, except that you need something square and square root. little bit slightly more messy, but the same proof, no difference. Okay. Hmm? Better do it. Huh? Okay. So, okay. Now I want to prove the completion is unique. For that, I need the following proposition. Okay. If X metric space, X, Y metric spaces, okay, spaces, Y is complete, assume Y is complete, okay, and A contained in X, some set, okay, and F from A to Y is uniformly continuous. There are so many uniformly continuous. Then there exists a F bar unique. There exists a unique F bar from A bar, A closure to Y, such that uniformly continuous, which is also uniformly continuous, and F bar restricted to A is F. Okay. It just says that every uniformly continuous function has a uniformly continuous extension to the closure, provided the range is complete. The range has to be complete. Okay. The proof is very simple. You know how to do that. Uniformly continuous function takes Cauchy sequence to Cauchy sequence. Okay. That's what we want to use. So we have a function defined on A. We want to define it on A closure. A closure is just the limit of all sequences in A. Right? Right? A closure is just limit of all sequences in A. That is the definition of A closure. So we want to define it on A closure. So X is in A closure. We want to define the function, extend the function to A closure. Okay. So this X is in A closure means there exists Xn in A such that Xn converges to X. Okay. That's what it means. Okay. Okay. Now we want to say that the limit exists. Okay. Now Xn converges, so Xn is Cauchy. Okay. Now uniformly continuous means f of Xn is also Cauchy. Exercise. Exercise. Xn is Cauchy. Continuous function will take converging sequence to converging sequence. Uniformly continuous function will take Cauchy sequence to Cauchy sequence. Okay. It need not, continuous function need not do. For example, X is Xn 1 by n. I mean, in this interval 1 by n. Okay. Something can go to 0. Some function, some sequence can go to 0, but 1 by Xn, which is a continuous function, will not go to 0, will not converge. So it will not be a Cauchy sequence, right? Xn, some Xn can go to 0, which is a Cauchy sequence, but the 1 by Xn will not be Cauchy. So if that means the function 1 by x going to 1 by x is not Cauchy. Huh? X going to 1 by x. The function 1 by x is not Cauchy. So continuous function need not take Cauchy sequence to Cauchy sequence. Okay. But uniformly continuous function will take Cauchy sequence to Cauchy sequence. Okay. So Xn is Cauchy. I mean, this is exercise, very easy exercise. Okay. No, you don't need to submit. You just, but when, if I ask this question in the exam, you have to write this proof also. Okay. This is very easy. There's the same way you prove that convergent sequence take exactly same definition, epsilon delta definition, if you just use, except that there exists a single epsilon, single delta for all epsilon, all x, okay, because of that. Okay, this is Cauchy. So the, since y is complete, since y is complete, there exists f of x in a closure such that f of xn converges to f of some, I mean, f bar x. You want to call it f bar x, f bar x. Okay, f bar x is defined. We have to show it's well defined. There exists f of, I mean, we want to define our function on x, which is in x bar, a bar. Okay, I take a sequence in A which converges to x. because it's Cauchy, f of xn is Cauchy, then because y is complete, f of xn will converge to something. So I take that f of x, that call that as f bar x or whatever. I define f bar x to be the limit of f of xn. But there may be two sequences converging to that. Okay, I have to show that it is well defined. Okay, there may be two sequences converging to that. So suppose, maybe I'll write it on the top. Now suppose yn also converge to x. Okay, we have to show that the limit is same. You can do it by using epsilon delta, but there is a very easy trick. You just write a sequence x1, y1, x2, y2, like this, x and y. This sequence, just insert this sequence. Okay. Since xn converges to x, yn converges to x, this sequence will also converge to x, right? Okay. That implies f of x1, f of y1, which is also a Cauchy sequence, because that is Cauchy convergent, that is Cauchy, this is also Cauchy. Okay. This will also will have a convergence. This will also converge to something by the same argument. But then I am just whatever it's called, whatever that process is called. Okay. I'm just writing like this a sequence. I have a sequence xn, I have sequence yn. I am proving that that limit is well defined. Okay. So I am just writing it like this. It is just an argument. There is nothing in this. Okay. Xn and yn both converge to x. Then if I arrange it like that, that will also converge to x. Okay. So from that it follows that this will converge to f of x. Okay. I mean, this will converge to something, but it has to converge to f of x because there is a subsequence which converges to that. Okay, this converges to f of x. Since a subsequence, since both the subsequence f of xn converge to f of x. Okay, I am not writing all the argument. Okay, but you better note that. Okay, this is converging to x. Okay, that's very clear because both of them, and this is Cauchy. So this converges, but this converges. So, but there is a subsequence which will converge to x, f of x. So this has to converge to f of x. So it is well defined. I mean, f bar x, whatever. Same, it's well defined. If you want, you call it as y and then do this. I called it f of x. Maybe you call it, I mean, before defining f of x, it's better not to define, call it f bar x or something. Okay, this is a misuse of notation. You can call it y and finally define, call that as f. Is it okay what I did? Okay. Okay. Now we got something. And it is unique, which is clear because it is determined by the limit, right? It's unique. I mean, I leave it as an exercise. It's unique. That is clear. What else we need? Do we have to prove anything? That's all I think. Since a subsequence f of x and converges to f of x. Okay. F bar x. No, this is f bar. F bar x. Since a subsequence converges. I mean, the sequence converges and the subsequent converges f of x, so the limit should be f of x. Okay, that is the argument. Okay. Since I am recording everything, I am not writing everything. Okay, you can write it from whatever. Okay. So this proves that we have a unique limit and that this f bar is uniquely, I mean, this f bar is a unique extension. If there is any extension, that has to, I mean, any for some sequence, it has to be defined like that. For any extension, if G is something, G is such that G is continuous, I have to prove that it is uniformly continuous. That's the only thing remaining. Okay. So now to prove f bar is uniformly continuous, I forgot to prove that. Okay. Uniformly continuous, we have to prove. Okay. Now first, f is uniformly continuous. That is given. That implies for all xy, x and y, and epsilon. I mean, for all epsilon greater than, given epsilon greater than 0, for epsilon greater than 0, and for all xy, this is true. D of xy less than delta will imply D of f of x for all xy in A. I mean, f is uniformly continuous in A. we want to prove that F bar is uniformly continuous and A bar. Okay. So F is uniformly continuous means given epsilon, for epsilon greater than 0, for all xy, we have this less than delta will imply f of x, f of y. I'm using the same d for both of them, maybe d1, d2. Please don't worry about it. Okay. This is less than epsilon. This is for all xy in A. Yeah. F of, yeah, A bar, f of f bar x. X, sorry, f of A. No, in A, sorry, you are right. Yeah, A bar.
We don't fail.
No, there exists, since y is, no, this is right. Since y is complete, there exists f of x bar x. Huh? No, f of x in y, sorry. Sorry, this is I mean, since y is complete, there exists a consequence as a limit. I'm sorry. Yeah, this is okay. Okay. Now, where are we? Yeah, proving uniformly continuous. F is uniformly continuous. The extension is also uniformly continuous. F is uniformly continuous. The definition is this. Okay. Now, we want to prove the extension is also uniformly continuous. Okay. I want to say that the same delta works for epsilon. Okay. So, let epsilon greater than 0. And now we choose xy in A bar. Okay. Xy in A bar and xn, yn both contained in A such that xn converges to x, y, because they are in A bar. Okay. Then we know we have already proved the metric is continuous. So d of xn, yn will converge to d of xy. Okay. Right. This is okay. Okay. Now, if d of xy is less than delta, okay, then d of xn, yn, I just give a, I mean, this argument is correct, but then I don't write each and everything, is less than delta of, I mean, this is my usually my symbol for sufficiently large, not for all, but after some time. This is a very useful symbol. Okay. You understand what I mean? I do like this. Sufficiently n, large n, after sufficiently large n. Maybe after some, except finitely many of them, after that, this is a symbol. You can fix your notation and work in a course. As far as it is understood, it's fine. Okay. You should mention it. That's all. Okay. You can write any notation you want. If we, I mean, I may not have chance to use it many times, but if you want, or otherwise you say that after some time, for eventually. Okay. That's what it means. Eventually. Eventually, after some time, this is less than delta. Okay. So this implies d of f of xn, f of yn is less than epsilon because of uniform continuity. We are assuming that for that. Okay. Now this will converge to d of x, f of y. Sorry, f bar f bar y. Okay. But this should be less than. That's all. It's done. If you want, I repeat the argument. I want to, f is uniformly continuous. I want to prove the extension is uniform continuous. So given epsilon, I choose a delta for this f. Okay. Now I say that the same delta works for the same epsilon. Okay. Now if you have an epsilon greater than 0, I choose x and yn which converge to x and y. Because of that, the metric will converge to this. Okay. Because of now, if this is what we have to prove, dxy less than delta, then this is less than epsilon. That's what we have to prove uniform continuity. Okay. Now this is less than epsilon. So this is less than, I mean, this is less than delta, this will be less than delta. But because x and yn are in A and f is uniformly continuous already, that's how this is less than epsilon, but this will converge to this is less than epsilon. Okay, fine. That's all. Okay. So I have proved this. Just I have to prove the completion is unique, okay, using this. Yeah, question. Here. The point is to prove that it is, you have got a candidate for You call it y if you want. You have a candidate that is well defined. For two different sequences, it has to be same. Okay. Now, which was left out in the earlier statement, completion. I have to leave at 15. So I want to give another construction of completion, but I will not have time for that. So I will just prove completion is unique. Okay. Completion of a metric space is unique. You have seen this proof? You have seen this proof? You have seen that proof? You haven't seen that? Huh? This one you have seen? Okay. You have seen means it was done in the class or you have seen in some book? Huh? It was in a quiz. Okay. Have you seen this? Completion is unique.
This was there as a homework.
This was there as a homework. Okay, this is very okay. Means completion is unique means what? Okay. So HD is a metric space. X is a, I mean D is everywhere. Corresponding D I will use. Okay. And suppose Y, sorry, X1, X2 are complete. Okay. X1, X2 are complete metric space. Okay. Such that there exists phi1 from X to X1, phi2 from X to X2 are isometries. Okay. Such that phi1x contained in X1, phi2x. I'm just writing the meaning of completion is unique. Okay. Phi2x contained in X2 are dense. I mean, that is what completion means, right? Completion means X sits inside some other place, some other complete metric space by a isometry like this. Okay, that's what it means. Okay. Then there exists a single free from X1 to X2 such that P of P1 is P2. Okay. You just think about it, there is nothing in that. It is just saying the completion is unique. Completion is unique means by uniqueness we mean we identify two metric space if there is an isometry between them. Okay. So this is also isometry, I should say. Isometry is something which preserves the distance. There is a bijective isometry. I mean, this is on to, isometry is always on one. If it is on to, is fine. Okay. This is, yeah. Okay. This is a bijective isometry. Okay. So it is, I mean, if X1 is, this says that if X1 is one completion, X2 is one completion, then there is an isometry between X1 and X2. That's what this says. X1 is a completion means X1 is a complete metric space and there is a phi1 from here, which is an isometry, and phi2 from here, which is an isometry. Then there exists, I mean, then such that they are dense there. That's what completion means. Okay. Then there exists a phi from X1 to X2, which is an isometry, such that it takes this phi1x to phi2x. Okay. That's okay. Proof. Phi1 from X to X1 is an isometry. So I take it as phi1 is on to is bijection. Okay. Huh? Which is identity function? They are not identity function. That is an isometry. Yeah, they are just identity function. Yeah. If you identify their identity function. After your identification, it is identity, right? Hmm. Hmm. Here, phi 1 is a function. Phi 1 is from here to here. This is just composition, if you want, okay? There is no proof. Here, phi 1 is from x to phi 1x. This is contained in x1, right? I'm just taking it to the range, restricting to the range. When you restrict to the range, it is onto. That's what I'm saying. There's nothing else. So that I will take an inverse. Okay. Now, phi 1 inverse is from phi 1x to x is a bijection, right? So if we apply phi 2, this is a bijection, right? This is the bijection. This is an isometry. The bijection onto isometry, right? So from phi 1x to phi 2x, there is an onto isometry. Isometry is uniformly continuous. Okay. Isometry, which is also uniformly continuous. That means it's uniformly continuous. It satisfies the definition. Okay. Now there is an extension between them. Phi 2 compose phi 1 inverse. Phi 1 inverse will get you to x. Then you apply phi 2. Then I initially wrote x. Then I wrote the phi 2. Okay. So this is uniformly continuous. So there exists a function from uniformly continuous function from the closure to closure. That is, so there exists a phi from closure. The closure of this, right? This is the closure of this is this, closure of that is this. Okay. And that will be isometry will be clear because it is just the it's not composition of isometry. Here it is composition of isometry. It is just the limit of, I mean, you have an isometry, it is extended by limits, right? Xn will converge to xn, yn will converge to yn, then phi of xn, phi of xn, yn will converge to phi of xy. So that will also preserve the distance. Okay, I will write it. Okay, there exists such that phi of, I mean, this is an isometry. By definition, that will take phi of phi1x will become phi2x by definition. You just check it. Okay, this is a very easy exercise. Since when you were younger, you have solved those exercises, so you should solve this. Okay. Now you are more mature, you should be able to solve. Now this is very easy, just definition, write down the definition, there is nothing. I have given all the ingredients, okay.
But I can't understand it now.
Just have more questions, okay. Just sit down, write down, everything is written. You just have to verify that. It's a good exercise to verify this, okay. It's very easy. I have to leave, unfortunately, so I will.